Here are two simulations that we'll be discussing throughout this entire video for us to understand better about polarization. And so in this video, we'll be discussing about the microscopic theory of dielectrics. And so before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion, as well as the timestamps for you to skip throughout this video. So let's jump straight away into the idea in which we have already discussed from the previous video, which is the molecular field. So the molecular field is the electric field at a particular molecular position after you remove that one particular molecule. So let's say, for example, if you have a dielectric and you want to figure out the molecular field here, that means that you just need to remove this molecule and figure out the electric field. It's that simple. But the way that you do this is it requires some physics in order to figure out what's the electric field at that particular position, disregarding that particular molecule. So the way that we'll be doing this is by thinking of a way for us to generate a electric field in here from the outside, and a method that we'll be doing that is by using a infinite plate, just to make sure that the E vector is constant. So there will be a positive buildup and a negative buildup here. There is also going to be a polarization in this direction, which means that there will be positive buildup and negative buildup here. And we could also try to remove a sphere from the dielectric, in which this will later be having the positive terminal here and the negative in here. And lastly, you just need to put in the extra molecules for you to fit in, except for the last molecule that you don't need to put in. So there's the four different components for the molecular field is gonna be the electric field from the outside, E vector from the two parallel plates, and then you add it with the E vector from the dielectric, or technically this outside surface, and the inside surface, we will call that as ES. And lastly, it's the one inside the empty space, which we'll call that as EI vector. So let's try to find a much more better definition for each of these E vectors. So EX vector is the one from the outside, and you would know that this E vector only from these two capacitive plate, it's going to be sigma over epsilon 0. This is something that's very well known. For the ED vector, it's going to be, well, in here, well, first of all, what I need to discuss is that the direction, this thing goes in the positive x direction. And then for the ED vector, the sigma in here will be p dot n hat, or in here, it's just p. So that's the sigma from the polarization. So it's sigma over epsilon 0, but the direction is actually negative. So I forgot to mention that this is the positive terminal, this is the negative terminal. So in here, there would be the ED vector in this direction, right? So it's the x hat, and then we'll have the ES vector and the EI vector, which we'll compute later on. So, okay, sorry, so this should be the P vector. So we can just simplify it as something like this instead. So now, we could actually try to consider something else. This thing here is when we consider the capacitive plate, and we assume this to be just to be a vacuum. But in actuality, it's not, and a much more reasonable thing for us to measure is not the EX vector, but it's the E vector, the total electric field instead. But in here, we also play with boundaries. So instead of thinking about the E vector, we should think about the D vector instead. The displacement vector, it's going to be the sigma in the x hat direction, like so. And so if we know about the D vector to be sigma x vector, this is the same thing as epsilon 0 E vector plus the polarization P vector. So if you rearrange this, you would get this component here. So this is just E vector plus ES vector and EI vector. Okay, so that means that we can already straight away measure what's the E vector straight away. That's simple. We don't need to know about the polarization as well as the sigmas. But now ES vector is still something that we don't know as well as the EI. So let's discuss about the ES vector. So we would have this thing to have the positive side here and the negative side in here. And let's call this to be A and angle theta. So we only want to figure out the electric field at the center here. And solving for it, it's quite simple. I mean, if you already know about the potential method, you could just express it in terms of the potential first, as well as the surface charge. And if you do the integral, it's gonna be the integral of sigma r vector over 4 pi epsilon 0 r cubed over the area, because this is technically the surface integral, or the ds in here. Let's just write that as, no, dA, because it's not a vector. So we can try to figure out what's the surface charge density. It's just gonna be p dot n, right? And the n hat in here points inwards because the polarization is coming from outwards, right? So the charge is gonna be, this is negative r hat. So it's gonna be negative p cosine theta. And so if we try to plug all of the values in and try to do the integral, we notice that the r doesn't change. So therefore, r is basically a. So this is 4 pi epsilon 0 a squared. Let's just put in a cubed first, and p, negative p, and the integral of the cosine theta, and then the r vector, it's going to be a cosine theta, and lastly the dA. The dA can be found just by figuring out what's the area for a sphere, technically, in terms of the integral form. If you have something like this, if this is theta, you would notice that this is a d theta, and this thing here is a cosine theta d theta. Sorry, this thing is supposed to be sine theta instead, my bad. So it's gonna be a squared sine theta d theta d phi. And the boundaries is gonna be coming from 0 to pi for theta and 0 to 2 pi for the phi. And because the function is not dependent on phi, we can just switch it and just do the integral straight away. It's going to be giving us the negative p over 2 epsilon 0, and the a is going to cancel each other out. So it's just the integral from 0 to pi of cosine squared theta sine theta d theta. So if you try to solve this integral, this is like cosine cubed theta negative over 3. Plugging 0 to pi, this is going to give us negative 2 over 3, negative p over 2 epsilon 0. Oh, sorry. I think I've missed a negative. Yeah. So the r vector is actually a cosine theta, right? But in here, it's just the a. I mean, technically, it's actually negative a. And the reason for this is that we are directing this from the charge towards the particular point. We don't do it the opposite way. Therefore, that's why I missed out a negative. So this would be positive. This integral is actually positive. So if you do it properly, you're going to get something like this, or it's p vector over 3 epsilon 0. So that's the e vector. So we are able to obtain that the em vector is e vector plus p vector over 3 epsilon 0. But what about the electric field from the molecules inside the cavity? And so some models that I want to share include when the polarization, sorry, when the polar dipole moment is parallel to each other, but it's randomly distributed. What we can do is that we can try to compute for the average E vector. And so the way that we'll do this is quite simple. So we can just try to consider when there's only one. And the formula for this, as long as you know that there's a polar dipole moment, the effect for the E vector in here, it's just gonna be a negative 1 over 4 pi epsilon 0. Multiply this by p vector over r cubed minus 3 p dot r vector over r to power 5. So if we try to consider only in one direction, let's say ex, it's just going to be negative 1 over 4 pi epsilon 0 of px over x cubed minus 3 of pxx plus pyy plus pzz times the a vector. Divide that by x to the power, sorry, r to the power 5, my bad. So, sorry, this should be the x vector. So, if you try to figure this out now, like this is technically x, sorry. So if we try to check now that this right-hand side here, it's going to be having negative 3px x squared and some py xy and pz xz. Now, if we assume that the distribution is random, we can straightaway determine what's the average. So x squared, and we're assuming this to be isotropic, so in any direction it's the same. X squared is going to be same thing as the average in the y squared, same thing in the z squared, which means that it should be the average of r squared as well, right? It's r squared over 3. That's something that we can figure out first. Something else that we can determine from the average is that x times y, because the average could be positive and negative, it will later cancel each other out. So xy is going to be 0, and also the other families of the heterogeneous variables. So therefore, if you simplify this, it's just going to simplify into a negative 1 over 4 pi epsilon 0 of, let's say, in the x direction. It's going to be straight away be 0. And it'll be true for y and z as well. So this is an interesting clue, is that the electric field from the inside of the cavity won't have an effect as long as it's randomly distributed. But you could also consider the case when it is very uniform. And in here, I'll be assuming that this will be a simple cubic type of interaction. So if you have, let's say, polar dipole moments, and they are still parallel and the same value, but they are uniform. What we can do is that we can try to compute what's the E inside now. So the E vector inside, it's going to be contribution from each of the components here. So let's just consider, let's say this like this A, and we'll just consider the one in this direction. So this means that there will be 2 of these, and the contribution is negative 1 over 4 pi epsilon 0. Same thing, it's p vector over r cubed over r cubed. Technically, this is a cubed because the distance here is a. And so this will be subtracted by p dot a vector, and there's an a vector outside, divided by a to the power 5. And this is only for one of them, but there will be some other contribution from the top and the bottom as well. But their values might be slightly different. So technically, this is not a vector. If we are only assuming the one in the x direction, it's just going to be ax hat, like so. So this is what I'll be assuming in this case. But then later, we will also consider the one in the y and the z, which is also the same family, right? But if we try to consider this, we figure out something first. Is that you could actually just get rid of the 2 and the 4 pi epsilon 0 on the outside here. You could just bring it all outside. So it's just a summation of the vectors from each of the x, y, and z. And considering that p vector over a cubed is something, and there will be 3 of these later on, and then you subtract this by each of these. Now, something that's interesting about this is that for the very first component, it's just a px, right? And then this is in the x hat direction. And then there will be another one, which is, oh, actually the a and the a would cancel each other out at the bottom, so it will be just a cubed, just to make it simple. So same thing for the y, it's going to be py y hat, and lastly for the z, it's pz over z hat, and technically there's 3 here, I forgot, like so. And so what we observe here is that this is also p vector. That means that this would evaluate to 0 as well. So we see that we could actually just assume that ei vector is actually 0 if you do a certain modeling, like if it's uniform or if it is randomly distributed, as long as they are having the same value in the same direction or parallel. So we get the idea that em vector is gonna be the e vector plus p vector over 3 epsilon 0. So the fact that I introduced the molecular field is that we want to relate this with the molecular polar dipole moment. So if we assume this to be linear, there's going to be a constant at the front, which we'll call this to be the polarizability. 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 And so if you try to notice what's the relationship between the molecular polar dipole moment as well as the polarization, it's just npm vector is equal to this big P vector. So what we can obtain here is that so the P vector is n alpha E vector plus P vector over 3 epsilon 0, right? So, and also in here, we also assume that technically the polarization is linear to the electric field, in which you know this to be k minus 1 epsilon 0, or this is also known as the susceptibility. So plugging that in, you would get this to be k minus 1 epsilon 0 is equal to n alpha of 1 plus k minus 1 over 3, right? And so if we simplify everything and try to get alpha, you would get that alpha is 3 epsilon 0 over n, and it's going to be k minus 1 over k plus 2. Now, what we derived here is something that is very useful in material science. It's something which we call as the Clausius-Mossotti equation, and this relates the dielectric constant with the polarizability, which is a microscopic property. So we discovered the idea that the polarizability is going to be related to the dielectric constant. And so if we are able to obtain what's the polarizability, we can determine what's the dielectric strength, which is something that is still strange for us if we don't know anything about electromagnetism. So let's try to figure out what's the source of the dielectric constant or the polarizability. We'll think of two different models. First, we'll be thinking about the induced dipoles. And so these induced dipoles, if you know from chemistry, it basically comes from a nonpolar molecule like hydrogen, oxygen, carbon dioxide. They are all nonpolar as well as the noble gas. But if you apply an electric field here, you would observe something. Like if we assume that the cloud of electron here is like it cannot be deformed, like what would happen is that this positive nucleus is going to shift, trying to find its stable equilibrium. So in here, I'm showing you the induced dipole mechanism for a certain type of atom in which you can see that the nucleus is moving while the electron cloud is not moving. I mean, it has remained constant. And you can see the colors, it is pretty much indicating the potential. So how to read this diagram here is that, so basically the nucleus wants to go towards the lower potential. And this is because that energy is just QE. Potential energy is Q times the electric field. Sorry, it's Q times the potential, my bad. So if you have a positive, that means that if you want to minimize U, you need to minimize the change of the potential. Sorry, it's actually technically just potential, but it's normal for me to write it as the change of potential. So how do we solve this? There are multiple ways for you to solve it. In here, I'm going to be showing you a method by solving the electric field. So we'll be solving a case where electrons are evenly distributed along a sphere. So it has a charge of Q, which is Z times E. E is the elementary charge. So you could get what's the volume charge density. It's just ZE over 4 over 3 pi r cubed, where this will be called as the big R. So therefore, if we want to figure out what's the electric field in here, we can use something which we call as the Gauss law. We have already discussed about this. So the closed surface integral of E vector dA vector is going to be the same thing as the Q enclosed, divide that by the epsilon 0. Since in here I'll be assuming this will be a vacuum, it's epsilon 0. So if we try to solve this, we know that it has symmetricals. It has a symmetry. Therefore, if we define E vector to be just in the radial direction, it's E times the area, which is 4 pi r squared. Yeah, 4 pi r squared. So this distance here is r. This would equal to the Q enclosed, which is this guy. Multiply that by volume because it's uniform. So it's negative ZE over r cubed like so. And you divide it by epsilon 0. So what you would get is that the electric field in the r direction is going to be negative 1 over 4 pi epsilon 0 ZE times r cubed over r cubed, like so. Oh, sorry, it's r over r cubed. So something to notice here is that if we denote this r here to be the stable, a distance, let's call that to be x. So x would be stable, like so. So that means that the force from the outside added with the force from the molecule must be 0 for it to be stable, right? And the force from the outside is just the charge, which I'll denote that to be, yeah, we can call that to be big, to be small q, like we'll call the nucleus to be small q, times the electric field, which is equal to negative q of the electric field generated by the molecule. And it turns out that we obtain this E vector to be, so this is like the EM vector because technically it's like that. It's like if you remove everything except for the molecule, you would have that molecular field. It would equal to 1 over 4 pi epsilon 0 r cubed, and ZEX is something which you would already know to be the polar dipole moment. If this is x, this is the charge, ZE, this would mean that it's like a polar dipole moment here. And the reason why we could actually do this thing, I mean like especially for the distance, is that because this is actually this is like the center of charge. And the center of charge is at the center of the sphere. So therefore, if you shift your nucleus an x amount, the polar dipole moment is just Zx. So you get something like this. So you could now obtain what's the polarizability. The source of the polarizability, which is coming from this Coulomb's law, is 4 pi epsilon 0 r cubed. So what you could do now is that if you have a noble gas and you want to figure out what's the Bohr radius, technically it's like the effective radius, you could just measure the dielectric constant by using the Clausius Mossotti, get the polarizability in order to obtain the radius. It's a very elegant tool, and that's only for the induced dipole moment. So if we can see here from the picture, no, sorry, from the simulation, you would see that the polarizability is actually constant. Unless if I change the radius, of course. But in here, I don't change the radius. So what you would see is that it still has the constant polarizability, showing its sign doesn't really change because of the electric field given to it. So we discussed about the nonpolar. But what about the polar molecules? Now this is something that is much more interesting. Let's just try to solve it. So first of all, we need to understand where does the polarization comes from for polar molecules. And the idea is that if you have a liquid with polar molecules, it doesn't have any polarization because the molecules are randomly oriented. So therefore, the polar dipole moments will later cancel each other out. Thus, the polarization here, which you know the formula to be 1 over delta V of the sum of the polar dipole moments, is going to be 0. But when you apply an electric field, it's going to try to align with the electric field in order to minimize the energy. That's why you get polarization in polar molecules. It's just adjusting. And if you think about this, there should be a saturation point. So the saturation point is when all of the polar dipole moments face in one direction, right? So we can try to count this for a certain volume, which we'll call that as n, like this change of, or the small volume here. So polarization, the saturated polarization is going to be the amount of polar dipole moment within a given cell. That's going to be big N times the polar dipole moment, molecular polar dipole moment. This would give you the saturation polarization. But we need a much more better way. We need to know for certain temperatures, because temperature gives you random motion. So it's not exactly the saturated polarization that you would get. So how would you do that? So I'll be introducing some thermal physics and some statistical physics, but this is quite simple. So from thermal physics or from statistical physics, you would know that the probability to find something in a certain energy is proportional to e to the power of the energy over kT. Technically, it's the negative. So when the temperature rises, what you would see is that the this value would keep going down towards a value near zero. And so this would basically mean that for a given distribution of energy, like the E wouldn't really matter, so therefore the probability is like constant. So technically there is like there's a normalization constant at the front. And so if you try to consider this much more further, E vector here is actually kinetic energy. I normally write this as T, as well as the potential energy U. And you would know what U is. U is just negative P dot E vector, or the EM vector in here, the molecular field. Or we could simplify this to be negative PM EM cosine theta. And T here is going to be, it's not going to influence the probability. The main reason for, sorry, so let's just write this as EK because there's temperature. So actually, this thing should be EK instead because we already write what T is. T is temperature. So what we can do is that we can actually neglect EK. And why do we neglect EK is that technically it depends on temperature, but something that it doesn't depend on is the angle here, or the electric field. And the reason is that this polar dipole moment, if you apply an electric field, there will be a force in this direction and force in the opposite direction. So this balance of force will cause this object not to change velocity depending on the electric field. Because in here we'll be discussing about changing the electric field instead of changing the temperature. Because in here we are only thinking of the idea of the change of the angles instead of changing E vector and PM, because PM is dependent on EM, right? Sorry, actually this is not PM, this is P0, or the initial polar dipole moment. So if we have something like this here, and this means that this will be proportional to e to the power of P0 EM cosine theta, right? Divide that by kT. So what I want to show you in this simulation, and so what you see here in the simulation shows you the probability of the molecule to be in that particular direction. The much more yellow it is meaning that it is much more probable. Compare that if you go towards the much more blue side. So we should try to figure out what is the average. So obviously we don't really care much about the particular direction for each molecule. We care about the average. So to compute the average, if you already have done quantum mechanics or even some statistics, the way that you do this is by actually multiplying your intercept value, which is P0 cosine theta, and the probability distribution, e to the power P0 EM cosine theta over KT. Divide this by the e to the power P0 EM cosine theta over KT. And we'll be doing the integral over the solid angle. The main reason is that we are discussing about angles in 3 dimensions. That's why we use solid angles instead of doing, let's say, for certain problems, they use x, sometimes they use velocity or something else. But in here, the problem is only about the orientation. So we call in the solid angle. And if you try to do the integral, I won't directly prove it. It's going to be P0 cotangent of y minus 1 over y. And that's basically the average. So what's y? Y is P0 EM over KT. And if you plot this, it's going to be something like this. So you could see this. So you could see the saturation angle here. No, sorry, not the saturation angle. But there is saturation here. But when y goes to 0, you could see that there's this part here which is quite linear. And so we could try to analyze what's this linear bit here. So you could try to expand this, and it turns out that the approximation is gonna be 1 over 3 p0y, or it's gonna be p0 squared em over 3 kt. And this is the average p0 cosine theta. Or you could call this to be the molecular polarization at that particular point. Now, therefore, what you could get from here is that you could get what's the polarizability. It's P0 squared over 3 kt. Now, what you observe from this one is that polarizability for polar molecules come from temperature as well as the polar dipole moment. And so, obviously, if you think if you have a nonpolar, you could put the P0 here to be 0, and polarizability from the polar is 0. So technically polarizability is additive. So you could add in the deformation, the one that's coming from inducing from the electric field, as well as the orientation. So like the alpha total could be denoted to be the one from the deformation polarizability, as well as the P0 squared over 3 kt, or the orientational polarizability. This is what we call as the Langevin-Debye equation. And this gives us a better idea on the polarizability with respect to temperature, basically. Finally, I want to discuss about the ferroelectricity. So ferroelectricity is basically permanent polarization. So we'll go back towards E vector m. The molecular field is E vector plus 1 over 3 epsilon 0 p vector. And consider when E vector is 0, but not the p vector. We could just say that there is still some polarization. So what we could get is this would be E vector m is going to be the same thing as 1 over 3 epsilon 0 p0 vector. So now this permanent polarization in here, there are lots of criteria for you to fulfill this thing. So now if you try to think about what is the polarization, as you know from the formula, it's going to be n alpha of the EM vector, right? And this EM vector is defined also to be n alpha 3 epsilon 0 p0 vector. So there's a recursion formula going on. Not really a recursion formula, but it's just a relation between p0 vector and p0 vector. And there's only two different cases for this happening. Like if you try to solve this, there is a case where p0 vector is 0. That means that it doesn't have any polarization, and that means that this is not a ferroelectric. So this literally means that a permanent magnet cannot exist. But if you try to consider when this is 0, and alpha over 3 epsilon 0 is 1, you could have a case where the p0 vector is non-zero. This is what we call as ferroelectric material, something like barium titanium oxide. This is ferroelectric, and actually it has a point where it doesn't become a ferroelectric anymore. When temperature goes above 120 degrees Celsius, it becomes a polar molecule basically. And there is a And there's a certain temperature when this barium titanate doesn't become ferroelectric, and that is when it is above 120 degrees, or when it loses its ferroelectric property. This is what we call as the Curie temperature. So we should try to study more about the ferroelectric. So if we try to plot the E vector and the P vector, when the E vector is 0, or when there's no external field, there is a polarization. So maybe if we try to apply uh, a electric field that is counteracting this polarization, what would happen? It turns out that it will try to decrease itself. So it will go here until it reaches a saturation point, something like so, where when it goes back, it will just go and rest here. So there is another permanent polarization, but in the opposite direction. And if you give it a forward bias, it's going to be doing something like this and goes back here. So you could see this hysteresis pattern going on. So I won't fully discuss about what is the coercive field, what's the remnant field. So I will leave that later when we discuss about magnetic materials. But for now, that's all for today's video, in which we have already understood better about what polarization is and another type of material which we call as ferroelectric. And so thank you very much for watching. Make sure to like and subscribe, and also share this to your friends who wants to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.